Have you ever seen Andromeda with your own eyes? Most people would say no. They imagine powerful telescopes, space agencies, or professional astronomers. But the truth is surprising. You may have already seen it without realizing it. On a dark, clear night, far away from city lights, Andromeda appears as a faint, blurry patch in the sky. It does not sparkle like a star. It does not shine like a planet. It looks small, quiet, almost unimportant. Many people mistake it for a cloud or ignore it completely. Yet that tiny smudge is an entire galaxy. Not a star, not a nebula, a galaxy. That is where the misunderstanding begins. Andromeda is visible without a telescope, yet almost nobody truly understands how big it really is. We hear facts like, it is 2.5 million light years away, and move on. The number sounds impressive, but it does not change how we feel. It does not change how we imagine it. In our minds, Andromeda stays small, distant, manageable. Images make this problem worse. Textbooks, posters, and online pictures show galaxies neatly framed, floating side by side in black space. Diagrams compare galaxies like coins on a table. Everything looks clean, organized, and scaled down so it fits on a page or a screen. These images are useful, but they quietly lie. Not because they're wrong, but because they hide the truth of scale. In reality, Andromeda is not just far away, it is unimaginably large. It contains hundreds of billions, maybe even 1 trillion stars. Each star is separated by enormous distances. Its visible spiral stretches across space so wide that light itself needs hundreds of thousands of years just to cross it. And what we can see is only part of the story. Most of Andromeda is invisible, wrapped in a massive halo that reaches far beyond its bright arms. When you look at Andromeda in the sky, you're not seeing a small object far away. You're seeing a gigantic structure, so large that your brain simply refuses to process it correctly. This video is about fixing that misunderstanding. By the end, numbers like distance and size will feel different. You'll no longer imagine Andromeda as a neat spiral in a picture. You will understand it as a vast, ancient city of stars, stretching across space on a scale that breaks everyday thinking. And once you truly grasp the scale of Andromeda, the universe will never feel the same again. When people hear the name Andromeda, a very specific image appears in their mind. A clean spiral, bright arms, a glowing center, floating calmly in black space like a painting hung on the wall of the universe. It looks distant, peaceful, and somehow complete, as if Andromeda is a finished object that can be fully understood just by looking at a picture. But that picture is not Andromeda. It is only a simplified shadow of something far larger, deeper, and more complex. In the simplest possible words, Andromeda Galaxy is a gigantic system of matter held together by gravity. It is a spiral galaxy, meaning its stars are arranged in long, curved arms that slowly rotate around a central region. Inside those arms are stars of all ages, glowing gas clouds where new stars are born, dark dust lanes that block light, and enormous empty spaces between everything. Nothing inside Andromeda is neatly packed. Everything is spread out across distances so vast that even light needs time to travel from one place to another. Andromeda contains hundreds of billions of stars. Some estimates suggest it may contain close to 1 trillion. Each one of those stars is its own sun, many with planets, moons, and systems of their own. When we say Andromeda is a galaxy, what we really mean is that it is a cosmic city, made not of buildings but of stars, and like any city, most of its space is not crowded. The distance between stars is enormous. If our sun were placed inside Andromeda, its nearest neighbouring star would still be light years away. Along with stars, Andromeda contains vast amounts of gas and dust. Gas clouds stretch across thousands of light years and slowly collapse to form new stars. Dust lanes cut through the bright spiral arms, hiding entire regions from view. These dark streaks are not empty. They are thick with material, blocking light like fog blocks headlights on a road. In visible images, these lanes look like scars. In reality, they are nurseries, places where future stars are quietly forming. But even all of this visible matter is not the full story. Most of Andromeda's mass is invisible. It is wrapped inside a massive dark matter halo that extends far beyond its bright spiral arms. Dark matter does not shine. It does not reflect light. We cannot photograph it. Yet its gravity controls how Andromeda moves, how fast it rotates, and how it interacts with other galaxies. Without dark matter, Andromeda would fly apart. So when we talk about what Andromeda is, we must understand that what we see is only a small part of what actually exists. This brings us to an important question. Why do we call Andromeda our neighbor galaxy? The universe is unimaginably large. Galaxies are usually separated by millions or even billions of light years. In that context, Andromeda is close. It is about 2.5 million light years away, which in cosmic terms is almost next door. Andromeda and the Milky Way belong to the same small family of galaxies known as the Local Group. This group contains dozens of smaller galaxies, but only two giants dominate it. One is Andromeda, the other is our own. Andromeda is not just a passive neighbor sitting quietly in the distance. Its gravity reaches far into space. It already influences the motion of nearby galaxies, including ours. Over billions of years, Andromeda and the Milky Way are slowly moving toward each other. This does not mean stars will crash into one another. Space is far too empty for that. But it does mean that, on the larger scale, these two galaxies are part of the same long-term story. Despite all this, most people imagine Andromeda in ways that are deeply misleading. They imagine it as a single object, like a giant spinning disk. They imagine it has a clear edge, where the galaxy ends and empty space begins. They imagine stars packed close together, glowing side by side like lights on a city street. They imagine Andromeda as something that could be held, measured, and fully seen if we just had a better telescope. None of that is true. Andromeda does not have a sharp boundary. Its stars thin out gradually until they blend into intergalactic space. Its dark matter halo stretches far beyond anything we can see, meaning the galaxy is much larger than its visible form suggests. It is not flat. It has thickness, layers, and streams of stars moving above and below the main spiral disk. Some stars orbit smoothly. Others follow stretched, tilted paths left over from ancient collisions with smaller galaxies that Andromeda absorbed long ago. Andromeda is not calm and static. It is active, evolving, and constantly changing, just on timescales far longer than human lives. Stars are being born and dying inside it right now. Entire star systems are drifting slowly across its vast interior. Ancient structures still carry the memory of past events that happened billions of years ago. Images and diagrams hide these truths. When textbooks show galaxies side by side, scaled down to fit on a page, they quietly erase distance and depth. When illustrations draw galaxies as clean spirals with sharp outlines, they turn something enormous and messy into something tidy and understandable. These images are useful for learning, but they train our brains to think small. In reality, Andromeda is not a picture. It is not a shape. It is not even just a place. It is a vast gravitational structure, spread across hundreds of thousands of light years, made of visible matter, invisible matter, motion, history, and time. Understanding what Andromeda really is means letting go of simple images and accepting that some things in the universe cannot be fully captured in a single frame. And once you begin to see Andromeda this way, not as a pretty spiral, but as a living, evolving galaxy, you are ready to confront its true scale. When people talk about Andromeda, the number always comes first. 2.5 million light years away. It sounds serious, scientific, final. Most people hear it nod once and move on. But here is the truth. That number does almost nothing for the human brain. In simple terms, Andromeda Galaxy is about 2.5 million light-years from Earth. A light-year is the distance light travels in 1 year, moving at the fastest speed anything can move in the universe. Light does not slow down. It does not rest. It moves constantly, covering about 300,000 kilometers every second. Even at that incredible speed, it takes light 2.5 million years to reach us from Andromeda. That fact is correct. But emotionally, it is almost empty. Our brains did not evolve to understand numbers like this. We understand steps, minutes, rooms, roads, and cities. We understand distances we can walk, drive, or fly across. When we hear 2.5 million, our mind does not build a picture. It simply shuts the door and labels it as very far. That is the distance trap. When scientists describe cosmic distances, they use numbers because numbers are precise. But precision is not the same as understanding. Saying 2.5 million light-years is like telling someone the ocean weighs a certain number of tons. It may be true, but it does not help you feel how deep or endless it really is. Try this instead. Imagine shrinking space so that the Earth and the Sun are 1 meter apart. In this model, our entire solar system fits inside a small room. The nearest star beyond the Sun would be several kilometers away. Our galaxy, the Milky Way, would stretch across a continent, and Andromeda would not be in the same country or even the same planet. It would be so far away that the model itself breaks down. You would need a map larger than Earth to place it correctly. Even that comparison still fails. We are comfortable with the idea of traveling far. People cross oceans in hours. Planes circle the globe in a day. Space missions reach the moon in a few days. Mars takes months. These journeys feel long, but they feel possible. They exist within human time. The distance to Andromeda does not. If you could somehow travel at the speed of the fastest spacecraft ever built, it would take tens of millions of years to arrive. Not generations, not civilizations. Entire species would rise and disappear before you even reached halfway. Mountains would erode, continents would move. Human history itself would be a tiny footnote in that journey. And yet, when we hear 2.5 million light-years, none of that appears in our mind. This is because our brains compress large numbers. Anything beyond a certain scale becomes emotionally flat. 1 million, 1 billion, 1 trillion all feel similar. They are just big. So when people hear the distance to Andromeda, they imagine it as far, but still small enough to fit comfortably into a diagram or a sentence. This leads to a deeper misunderstanding. Distance and size are not the same thing. Most people mix these two ideas without realizing it. They think that because Andromeda is far away, it must also be small in appearance or importance. Or they assume that understanding distance automatically means understanding scale. It does not. Distance tells you how long light travels to reach you. Size tells you how much space something actually occupies. A small object can be very far away. A gigantic object can also be very far away. Andromeda is both distant and enormous, but our brains collapse these two problems into one. We imagine a small spiral far away, floating neatly in space. This mental shortcut feels comfortable, but it is completely wrong. Here is another trap. We often compare cosmic distances to travel time. It would take millions of years to get there. But time itself becomes meaningless at this scale. 1 million years feels the same as 100 million years to a human mind. Both are simply too long. So the brain stops trying to understand. That is why numbers alone fail. They do not build intuition. They do not create feeling. They do not reshape imagination. Andromeda is not just far in distance. The space between us and it is filled with almost nothing. No cities, no landmarks, no reference points, just expanding space and faint radiation left over from the early universe. That emptiness itself is part of the scale problem. We are not crossing a road or an ocean. We are crossing silence. To truly understand Andromeda, we must separate two questions that are usually blended together. How far away is it? And how big is it? This part is about the first question, distance. In the next step, we will see that even if Andromeda were somehow closer, its true size would still overwhelm us. Distance hides scale, but it does not create it. For now, remember this. When someone says 2.5 million light-years, they're giving you a fact, not an understanding. And until we move beyond numbers and into comparison, time, and experience, Andromeda will remain a concept instead of a reality. This is why scale is so hard to imagine, and this is why the universe constantly feels smaller than it truly is. When people first learn about Andromeda and the Milky Way, they usually imagine two galaxies of roughly the same size, like twins drifting through space side by side. Textbooks often reinforce this idea by placing them next to each other in diagrams drawn as neat spirals with clean outlines. The message is subtle but powerful. Our galaxy feels familiar and important, so Andromeda becomes its distant but similar companion. Comparable, understandable, balanced. But this picture is misleading in ways that quietly shrink the universe in our minds. When scientists look closely, measure carefully, and step back from simple images, a much more unsettling truth appears. Andromeda is not just similar to our galaxy. In many important ways, it may actually be larger. To understand this, we first need to talk about what we mean by size. For everyday objects, size is easy. A car is longer than a bike. A building is taller than a house. These objects have clear edges. You can point to where they begin and where they end. Galaxies do not work this way. A galaxy does not have walls or borders. It does not stop suddenly. It slowly fades into space, becoming thinner and thinner until it is almost impossible to say where it truly ends. This single fact already makes comparison difficult, because size depends on where you choose to stop measuring. Even so, astronomers have developed ways to compare galaxies using their visible structure. When we look at the bright spiral arms, the glowing central bulge, and the dense star-filled regions, Andromeda stands out. The visible disk of Andromeda Galaxy stretches roughly 220,000 light-years across. By comparison, the visible disk of the Milky Way is about 100,000 to 120,000 light-years wide. Even at this first level, the difference is dramatic. Andromeda's visible structure is nearly twice as wide as our own galaxy. But width alone does not tell the whole story. A galaxy's size is not just about how far its spiral arms stretch. It is also about how much mass it contains. Mass determines gravity, motion, and influence. When astronomers estimate the total mass of Andromeda, including stars, gas, dust, and dark matter, the numbers become staggering. Current estimates suggest Andromeda may contain more total mass than the Milky Way. For a long time, scientists believed the Milky Way was the heavier of the two. More recent observations suggest Andromeda may actually outweigh us, especially when its vast dark matter halo is taken into account. This leads to one of the first major shocks in understanding cosmic scale. Andromeda is not just another galaxy like ours. It may be the dominant giant of our local region of the universe. When we talk about star count, the difference grows even more unsettling. The Milky Way is estimated to contain between 100 and 400 billion stars. That already sounds enormous, but Andromeda likely contains several hundred billion stars, and some estimates push that number close to 1 trillion. Imagine trying to count grains of sand on a beach. Then imagine several beaches stitched together into a continent. That is the difference we're talking about. And even these numbers are uncertain because stars are not evenly distributed. Many are faint, many are hidden behind dust. Many exist in regions we cannot see clearly from Earth. Now pause for a moment and consider what this means. If Andromeda were placed next to the Milky Way, star for star, arm for arm, halo for halo, it would not feel like a peer. It would feel like a larger, heavier presence. a galaxy that has swallowed more material, grown wider arms, and built a deeper gravitational well over billions of years. Yet the most misleading idea still remains. The idea of edges. When most people imagine galaxies, they imagine sharp outlines. A bright disk ends, and empty space begins. This mental image is reinforced by photographs which show glowing spirals surrounded by darkness. But that darkness is not empty. It is simply too faint for our eyes and cameras to detect easily. Galaxies fade. They do not stop. Beyond the bright spiral arms of Andromeda lies a vast halo of stars. These stars are scattered, dim, and ancient. They orbit far above and below the main disk, sometimes in long streams left behind by smaller galaxies that Andromeda consumed long ago. These stellar streams stretch across hundreds of thousands of light years, forming a ghostly structure that dwarfs the visible galaxy. And then there is the invisible part. Andromeda is wrapped in an enormous halo of dark matter. This halo does not glow, it does not emit light, but its gravity tells us it is there. It extends far beyond the visible stars, far beyond the spiral arms, far beyond anything we can photograph. When astronomers measure the motion of stars and satellite galaxies around Andromeda, they see the unmistakable signature of a massive unseen structure, holding everything together. This is where the idea of size completely breaks down for the human brain. If you define Andromeda's size by its bright spiral, it is already enormous. If you define it by its star halo, it becomes vastly larger. If you define it by its dark matter halo, it becomes something almost impossible to picture. Its gravitational influence stretches across a region of space so large that it overlaps with the outer influence of the Milky Way itself. In some models, the dark matter halos of the two galaxies may already be touching. This means that on the deepest level, Andromeda is not just bigger than we thought. It is bigger than we can easily describe. Now let us bring this comparison back to something familiar. We live inside the Milky Way. Every star you see in the night sky belongs to it. Every constellation is a tiny piece of our galaxy's disk. From inside, the Milky Way feels infinite. It stretches across the sky as a glowing band of light. It feels vast beyond imagination. And yet, when placed next to Andromeda, our home galaxy may be the smaller of the two. This realization often creates discomfort. Humans naturally center themselves. Our planet feels special. Our star feels important. Our galaxy feels like the main stage of the universe. But the comparison between Andromeda and the Milky Way quietly challenges this instinct. It shows us that even our entire galaxy is just one structure among others, and not necessarily the largest or most dominant. Andromeda's greater size also explains its future. Because it may be more massive, Andromeda plays a leading role in the slow gravitational dance between the two galaxies. Over billions of years, gravity is pulling them together. When they finally merge, Andromeda's mass and structure will strongly shape the outcome. The resulting galaxy will not be a simple blend. It will be a new system, influenced heavily by Andromeda's size and gravitational strength. But remember this: even now, before that future collision, Andromeda is already influencing us. Its gravity reaches across intergalactic space. Its dark matter halo extends farther than its light. Its size cannot be fully captured in any single image or number. This is the first true-scale shock. Andromeda is not just far away. It is not just another spiral galaxy. It is not simply similar to our own. It is likely larger, heavier, and more expansive than the Milky Way in ways that force us to rethink what big even means on a cosmic scale. And once you accept that galaxies do not have sharp edges, once you accept that most of their size is invisible, the comparison stops being comfortable and starts becoming humbling. Because if Andromeda can be this large, even while appearing as a faint blur in our sky, then the universe itself is far bigger than any picture, diagram, or number has ever allowed us to imagine. When most people think about galaxies, they imagine them as flat objects, a bright spiral drawn neatly on a black background, thin arms curling outward, like paint strokes on a canvas. This image appears everywhere, in textbooks, documentaries, posters, and online articles. It feels intuitive, it feels simple, and it is deeply misleading. The truth is that Andromeda Galaxy is not a flat disk floating in space. It is a vast three-dimensional volume, thick, layered, and extended in every direction. Thinking of Andromeda as flat is one of the biggest mental traps we fall into when trying to understand cosmic scale, because flat thinking collapses depth, hides distance, and shrinks reality into something our brains find comfortable. In reality, Andromeda has height, depth, and structure that stretches far above and far below the bright spiral arms we usually see in images. Those arms are not the galaxy. They are only the brightest slice through a much larger body. To understand this, we need to begin with why galaxies are so often shown as flat. The answer is simple. Light. The brightest parts of a galaxy are its dense star regions, especially in the spiral arms and central bulge. These regions glow strongly and show up clearly in photographs. When telescopes capture Andromeda, they naturally highlight what shines the most. Everything else fades into darkness, not because it is not there, but because it's faint. Our eyes and cameras have limits, so what we end up seeing is a glowing disc-like shape, and our brains quietly assume that this glowing shape is the entire galaxy. But it is not. Andromeda has thickness. Its central region is not a thin line, but a swollen bulge of stars extending tens of thousands of light years above and below the plane of the spiral arms. Around this bulge and disk exists a vast stellar halo, a spherical distribution of stars that surrounds the galaxy like a ghostly cloud. These stars do not sit neatly in a flat plane. They orbit in tilted, stretched, and sometimes chaotic paths. Some move far above the disk, then plunge back through it. Others remain in distant orbits, barely touching the bright inner regions at all. This means that Andromeda occupies space, not like a plate, but like a city suspended in 3 dimensions. Imagine a floating city, not built on the ground, but layered upward and downward. Streets above streets, buildings rising and descending, open spaces between structures. From far away, you might only see the brightest lights in the middle, but the city itself would extend far beyond that glowing core. That is what Andromeda is like. A luminous center, surrounded by layers upon layers of stars, all held together by gravity. Now consider depth. When we look at Andromeda in the sky, we see it as a flat shape because our eyes compress everything along the line of sight. Stars that are thousands of light years closer and stars that are thousands of light years farther away appear to lie on the same surface. In reality, Andromeda has enormous depth. Some of its stars are much closer to us than others. Some are far behind the bright core. Light from different regions leaves at different times and travels different distances before reaching Earth. The galaxy is thick enough that light crossing from one side to the other takes hundreds of thousands of years. This depth creates a powerful illusion. Because we cannot see depth easily, our brains treat Andromeda like a flat image. But depth is where scale truly hides. A galaxy that is wide but thin would already be impressive. A galaxy that is wide and thick becomes something else entirely. It becomes a volume of space, not a surface. Andromeda is not spread across the universe like paint on a wall. It is built into the universe like a mountain range floating in the dark. Above and below the main disk, stars continue to exist in large numbers. These stars are often older, dimmer, and more spread out. Some belong to ancient populations that formed early in the galaxy's history. Others were pulled in when Andromeda absorbed smaller galaxies long ago. When those smaller galaxies were torn apart by gravity, their stars did not vanish. They were stretched into long streams, and shells that now orbit far from the main disk, forming faint structures that extend Andromeda's volume even further. This is where the idea of thickness becomes impossible to ignore. If you could view Andromeda from the side instead of face-on, you would not see a thin line. You would see a thick band with a bright centre and a diffuse glow extending far above and below it. And beyond even that glow lies the dark matter halo, an invisible structure that defines the true outer boundary of the galaxy's influence. This halo is not flat at all. It is roughly spherical, extending in every direction, making Andromeda much more like a giant cosmic sphere than a spinning disk. Now let us talk about the space between stars. One of the most common mistakes people make is imagining galaxies as crowded. We see images filled with stars and assume they are close together. In reality, galaxies are mostly empty. The average distance between stars in Andromeda is enormous. Even in the dense regions, stars are separated by trillions of kilometers. In the outer halo, distances grow even larger. You could travel for years at high speed and pass nothing but darkness between stars. This emptiness is a critical part of understanding volume. Because stars are so far apart, the galaxy's volume is not filled with solid matter. It is filled with space, vast, silent space, with points of light scattered through it like islands in an ocean that has no shore. Andromeda's volume is defined not by what fills it, but by how far its gravitational influence reaches. This is why the flat spiral image fails so badly. It shows only where stars are most concentrated. It hides thickness. It hides depth. It hides the vast emptiness that actually defines the galaxy. When you imagine Andromeda as a flat disk, you unconsciously shrink it. You compress 3 dimensions into 2. You remove height and depth, and with them, you remove scale. In truth, Andromeda is layered. It has structure within structure. A bright central bulge, a thick disk, a thin disk embedded inside it, a stellar halo surrounding everything, streams of stars looping far beyond the visible edges, and all of this sits inside a massive dark matter halo that stretches farther still. Each layer adds size, each layer adds volume. Each layer pushes Andromeda beyond simple imagination. This realization forces a shift in thinking. Galaxies are not objects you look at. They are environments you exist inside. If you were inside Andromeda, you would not see a spiral. You would see stars scattered across the sky in every direction. The galaxy's shape would not be obvious. Its volume would surround you completely. Only from far away does the spiral pattern emerge, and even then, it hides most of what truly exists. So when we say Andromeda is large, we must be careful not to picture width alone. Its size is not just measured across its face, it is measured through its thickness, its depth, and the enormous regions above and below its bright disk. It is a 3-dimensional structure, occupying a vast region of space, far larger than any flat image suggests. This is the moment where flat thinking breaks. Andromeda is not a disk, it is not a plate, it is not a picture. It is a volume of space so large that light, time and gravity all behave differently within it. And once you truly accept that, once you begin to imagine Andromeda as a floating, layered city of stars rather than a glowing spiral on a page, your sense of scale shifts permanently. Because if a single galaxy can occupy so much space in 3 dimensions, then the universe itself is not just wide. It is deep beyond comprehension. When people hear how many stars exist inside Andromeda galaxy, the number sounds overwhelming at first. Hundreds of billions, possibly close to 1 trillion. It feels enormous, almost absurd. The mind reacts with a kind of surrender. That is too many to imagine, so it must already be enough. Surely 1 trillion stars should feel unimaginably large. But here is the strange truth. Even 1 trillion stars still feels small to the human brain. This is what we can call the star count problem. Numbers grow faster than imagination. Our minds evolve to handle dozens, hundreds, maybe thousands. Beyond that, numbers lose their shape. 1 billion, 10 billion, 1 trillion all collapse into the same vague feeling of a lot. The emotional difference disappears. So when astronomers say Andromeda may contain around 1 trillion stars, the statement sounds impressive, but it does not actually expand our sense of scale. It just adds zeros. To understand why this happens, we need to slow down and unpack what a star count really means. Start with one star, our Sun. It is massive enough to hold 8 planets, countless asteroids, comets, and an entire system of motion around it. Now imagine 2 stars separated by trillions of kilometers. Add another and another. Spread them out across space, not packed together, but drifting in vast darkness. That is how galaxies work. Stars are not piled up like grains of sand. They are scattered like distant islands across an ocean that has no visible edge. Now multiply that image not by 10, not by 1,000, but by hundreds of billions. Andromeda is not filled with stars, it is filled with space. This is the first major misunderstanding. When people imagine a galaxy with 1 trillion stars, they imagine crowding, bright points close together, a glowing mass so dense that stars almost touch. This image comes from photographs, where stars appear packed because we are compressing 3 dimensions into 2. Depth disappears, distance collapses. What looks crowded in an image is often separated by light years in reality. Inside Andromeda, the average distance between stars is enormous. Even in the dense regions of the spiral arms, stars are typically separated by several light years. In the outer regions and the halo, that distance grows much larger. You could travel for decades at the speed of our fastest spacecraft and never come close to another star. To make this relatable, imagine shrinking the stars down to the size of grains of sand. If each star were a grain of sand, the distance between them would still be measured in kilometers. The galaxy would not be a pile. It would be a desert, a vast, silent desert with grains scattered so far apart that you might walk for hours without seeing another one. This is why the phrase "1 trillion stars" quietly fails. It focuses on the count, not the spacing. Numbers alone suggest density. Reality delivers emptiness. Let us take another step. Imagine counting stars the way we count objects on Earth. You could count cars in a parking lot. You could count houses on a street. You could even estimate trees in a forest. But you cannot count stars in Andromeda that way. There is no cluster you can stand inside and see the whole. Stars exist across an enormous volume of space. Most of that volume contains nothing at all. No stars, no planets, just thin gas, dust and darkness. This emptiness is not a mistake or a gap. It is the normal state of a galaxy. Even though Andromeda may contain up to 1 trillion stars, the volume it occupies is so vast that stars make up a tiny fraction of the space. The galaxy's size grows faster than its star count. As galaxies expand, merge and evolve, they do not fill space. They stretch across it. The stars remain far apart, held together only by gravity's long reach. Now consider how misleading photographs can be. When we see an image of Andromeda, we see millions of stars at once. They appear layered on top of each other, bright and dense, but that image compresses depth into a flat surface. Stars that are thousands of light years apart appear side by side. Stars above and below the disk overlap visually. Our eyes interpret this as crowding, even though the stars themselves are separated by distances that would swallow entire solar systems. This visual illusion trains us to think of galaxies as busy and packed. In reality, galaxies are quiet, vastly quiet. If you were inside Andromeda, drifting between stars, you would not see a glowing spiral around you. You would see a dark sky with scattered points of light, much like the night sky from Earth, but richer and deeper. The idea of being surrounded by countless stars does not mean being close to them. It means being surrounded by emptiness that occasionally contains light. This brings us to another uncomfortable realization. Even 1 trillion stars are not enough to fill Andromeda. The galaxy's volume is so large that adding more stars does not make it feel crowded. It simply increases the number of distant points of light scattered across space. This is why star counts fail to convey scale. They ignore volume. They ignore distance. They ignore the fact that space itself is the dominant feature of galaxies. In fact, most of Andromeda's volume contains no stars at all. There are regions filled with thin gas, regions filled with dust, regions filled with dark matter, and regions filled with almost nothing. These empty regions are not small gaps between stars. They are enormous stretches of space where gravity still exists, but matter does not. Light travels through these regions for thousands of years without encountering anything solid. This emptiness is not a flaw. It is what makes galaxies stable. If stars were closer together, gravitational interactions would be violent. Orbits would be chaotic. Planetary systems would be constantly disrupted. The wide spacing between stars allows galaxies like Andromeda to exist for billions of years without tearing themselves apart. So when astronomers say Andromeda contains hundreds of billions or even 1 trillion stars, they're describing a galaxy that is mostly empty, not mostly full. This idea is deeply counterintuitive. On Earth, more objects usually mean less space. A crowded city feels tight. A packed room feels small. In space, more stars do not mean less emptiness. They mean emptiness stretched across a larger volume. This is why the star count problem is so powerful. It reveals a fundamental mismatch between how humans think about numbers and how the universe actually uses them. We expect large numbers to create density. The universe uses large numbers to create scale. Andromeda teaches us this lesson brutally. 1 trillion stars sounds like too many to imagine, yet it is still not enough to fill the galaxy's vast interior. The true scale of Andromeda is not in how many stars it has, but in how much space exists between them. The galaxy is not defined by its lights, but by the darkness that separates those lights. So when you hear the number again, pause. Hundreds of billions, possibly 1 trillion. Do not imagine crowding. Do not imagine closeness. Imagine distance. Imagine silence. Imagine light traveling for years without touching anything. That is what those numbers really mean. And once you understand that, the idea of scale begins to stretch beyond numbers and into something much more unsettling. Because if 1 trillion stars can still feel empty, then the universe itself is far more spacious than any number could ever suggest. Up to this point, everything we have talked about has been based on what we can see: stars, spiral arms, dust lanes, the glowing disk of Andromeda galaxy spread across space. Even when we talked about thickness, depth and star counts, we were still dealing with light. Dim light, distant light, overlapping light, but light nonetheless. It already felt overwhelming. It already felt too big. But now we arrive at the part of Andromeda that breaks scale completely, the part that does not glow, the part that cannot be photographed, the part that makes everything else feel small. This is the invisible Andromeda, the dark matter halo. To understand why this changes everything, we need to begin with a simple idea. Dark matter is matter we cannot see. It does not shine. It does not reflect light. It does not glow when it is hot. As far as we know, dark matter interacts with the universe almost entirely through gravity. We know it exists not because we see it, but because we see what it does. Stars move too fast. Galaxies rotate in ways that visible matter alone cannot explain. Galaxy clusters hold together when they should fly apart. Something unseen is providing extra gravity. That something is dark matter. Now here is the key point. In galaxies like Andromeda, dark matter is not a small addition. It is the main ingredient. The stars, gas and dust that we see make up only a small fraction of the galaxy's total mass. The majority of Andromeda's mass is dark matter. This means that most of the galaxy is invisible. The glowing spiral we admire is not the galaxy itself. It is a thin, bright layer floating inside something far larger and far heavier. Andromeda is wrapped inside a vast dark matter halo. This halo is not flat like the spiral disk. It is roughly spherical, extending in every direction far beyond the visible stars. If the visible galaxy were a city of lights, the dark matter halo would be an enormous, invisible continent surrounding it, shaping everything without ever being seen. How large is this halo? This is where scale becomes truly shocking. The visible disk of Andromeda is already enormous, stretching over 200,000 light-years across. But the dark matter halo extends much farther. Estimates suggest that Andromeda's halo reaches out more than 1 million light-years from its center. In some directions, it may extend even farther. This means the invisible part of Andromeda is several times larger than the part we can see. Let that sink in. Everything you think of as Andromeda, the bright spiral arms, the glowing core, the dust lanes, the stars, all of it fits inside a much larger, unseen structure. The galaxy does not end where the light ends. It continues silently into darkness, held together by gravity we cannot directly observe. This changes how we must think about size. If you define Andromeda by its visible light, it is already larger than the Milky Way's visible disk. If you define it by its stellar halo, it becomes even larger. But if you define it by its dark matter halo, Andromeda becomes something almost impossible to picture. Its true size stretches across a region of space so vast that it dominates the local group of galaxies. In fact, Andromeda's dark matter halo is so large that it likely overlaps with the dark matter halo of the Milky Way. This means that long before the two galaxies ever collide visibly, they are already interacting invisibly. Their halos may already be touching, pulling on each other through gravity, shaping the future of both galaxies billions of years in advance. This is a profound idea. The universe is not just made of what we see, it is mostly made of what we cannot see. Galaxies are not islands of light floating in empty space. They are concentrations of invisible mass with small bright regions embedded inside them. The light is the decoration. The dark matter is the structure. This is why galaxies behave the way they do. Without dark matter, Andromeda would not rotate as it does. Its outer stars would drift away. Its spiral arms would not hold together. The galaxy would slowly fall apart. Dark matter provides the deep gravitational well that keeps everything bound. And yet, despite making up most of the galaxy, dark matter remains mysterious. We do not know what it is made of. We do not know how it behaves on small scales. We only know that it is there, everywhere, shaping the universe silently. This makes Andromeda even more unsettling. When you look at Andromeda in the sky, you see a faint blur. But that blur is sitting inside a massive invisible structure that stretches across intergalactic space. The light you see is the tip of a gravitational iceberg. Most of the galaxy is hidden below the surface, invisible and vast. This forces us to rethink what it means for something to be big. We are used to judging size by appearance. A bright object feels important. A large image feels dominant. But in the universe, brightness is not the same as mass. The most important parts of galaxies do not glow. They shape reality quietly, through gravity alone. Andromeda teaches us this lesson with brutal clarity. The galaxy's visible size already overwhelms human imagination, but its invisible size overwhelms even scientific intuition. The dark matter halo extends so far that defining where Andromeda truly ends becomes almost meaningless. There is no sharp boundary, no clear edge, just a gradual thinning of gravitational influence that fades into the background of the universe. This means that when we compare Andromeda to the Milky Way, we are not just comparing two visible spirals. We are comparing two enormous, invisible structures, each wrapped in halos that dominate millions of light-years of space. The visible collision billions of years in the future is only the final act. The invisible interaction has already begun. This is the moment where scale stops being abstract and starts becoming disturbing, because if a single galaxy can possess an invisible structure this large, then the universe is not just bigger than we think. It is structured in ways that completely bypass human senses. We live in a universe where most of what exists cannot be seen, touched or photographed, yet determines the motion of everything we do see. Andromeda is not just a galaxy of stars, it is a galaxy of gravity. Its true size is not measured by light years of glowing arms, but by the reach of its invisible mass. And once you include that hidden component, Andromeda stops being a distant neighbour and starts feeling like a colossal presence stretching across space in silence. This is where scale truly breaks, because now we are no longer talking about what we can see, we are talking about what controls reality itself. And when you realise that most of Andromeda is invisible, that its largest component cannot be photographed, and that this invisible structure may already be touching our own galaxy, your understanding of size changes forever. The universe becomes less about images and more about forces, less about light and more about gravity. And Andromeda, once a faint smudge in the night sky, becomes a vast, unseen giant, quietly shaping the future of everything around it. When you look up at the night sky, it feels calm, ordered, and familiar. Stars appear as tiny points. The moon feels large and dominant. Everything seems placed neatly, as if the sky itself has been scaled to fit human vision. This sense of comfort comes from one simple illusion. Our eyes only show us what is bright. Everything faint is quietly erased. And nowhere does this illusion hide reality more effectively than with Andromeda Galaxy. Most people who know Andromeda exists imagine it as a small distant object, a faint blur, something you need a telescope to appreciate. Even those who know it is visible to the naked eye imagine it as tiny, almost insignificant compared to the rest of the sky. This belief feels natural because it matches what we see, but what we see is not what is actually there. In reality, Andromeda is enormous in our sky. The problem is not its size, the problem is our eyes. When astronomers talk about how large Andromeda appears from Earth, they use a concept called angular size. This describes how much of the sky an object covers, not how bright it is. By this measure, Andromeda is one of the largest objects in the night sky. Its visible core alone spans about 3 degrees across. When you include its faint outer regions, Andromeda stretches even farther. To understand what this means, we need a comparison. The full moon appears about half a degree wide in the sky. You can cover it easily with your fingertip held at arm's length. Andromeda's bright central region is already several times wider than the moon. When you include the faint outer arms, Andromeda spans an area of sky that can be 5 to 6 times the width of the moon. Let that sink in. If human eyes were more sensitive, Andromeda would not look like a tiny smudge. It would look massive. It would stretch across a large portion of the sky, dwarfing the moon in width. It would not be a point of interest. It would be a dominant structure overhead. So why does it not look that way? Because most of Andromeda is faint. Human vision is excellent at detecting contrast and motion, but terrible at detecting faint, extended light. Our eyes evolved to spot predators, read faces and navigate landscapes, not to detect dim galaxies spread thinly across the sky. Andromeda's light is not concentrated. It is stretched across hundreds of thousands of light years. That means the light arriving at Earth is spread out over a large area of sky, making each part incredibly faint. Cameras struggle with this too. Most photographs of Andromeda shrink it without anyone realizing it. They zoom in on the bright core. They crop out the faint outer regions. They increase contrast to make the galaxy stand out against black space. The result is a beautiful image, but a dishonest one in terms of scale. It turns a vast, sky-spanning object into a neat spiral that fits comfortably on a screen. This is why images quietly lie. They show detail, but hide size. If you could remove this limitation, If your eyes could see faint light as easily as bright light, the night sky would be transformed. Andromeda would no longer feel distant or small. It would appear as a giant, ghostly structure stretching across the stars. Its core would glow softly, and its spiral arms would fade gradually outward, like smoke illuminated by moonlight. The galaxy would not have sharp edges. It would blend slowly into the darkness, covering a huge portion of the sky. It would feel overwhelming. You would not see Andromeda as an object. You would see it as a presence. Imagine standing under a sky where a pale, luminous cloud stretches from one horizon to the other. Not bright enough to hurt your eyes, but bright enough that you cannot ignore it. Stars would appear embedded inside it. Constellations would be distorted and partially hidden. The familiar patterns we recognize in the sky would be interrupted by this enormous background glow. That is what Andromeda would look like at true scale. The moon would no longer feel dominant. In fact, the moon would feel small by comparison. Bright, yes. Sharp, yes, but small. Andromeda would be broader, softer, and far more expansive. It would not shine. It would loom. This is difficult to imagine because we are not used to faint things being large. On Earth, large things are usually bright or solid. Mountains block the sky. Buildings cast shadows. But Andromeda does neither. Its size is hidden in softness. Its scale is hidden in subtlety. This is why people underestimate it so badly. When something is both huge and faint, our brains struggle to register it correctly. We are trained to associate size with intensity. Andromeda breaks that rule. It is enormous but gentle, vast but quiet, spread thin across the sky instead of concentrated into a point. Even when you know this intellectually, it is hard to feel. So try this mental exercise. On a dark night, look up at the moon. Notice how much of the sky it covers. Now imagine 5 or 6 moons placed side by side. That is roughly how wide Andromeda truly is in the sky. But instead of a bright disk, imagine a soft glowing mist, fainter than clouds, fainter than the Milky Way band, yet large enough to stretch across your entire field of view. Now imagine that this mist is not nearby. It is not atmospheric. It is not part of Earth. Every photon reaching your eyes began its journey over 2 million years ago. The light left Andromeda before modern humans existed. It traveled through empty space for longer than human history, carrying the shape of a galaxy with it. And all of that light arrives gently, quietly, spread across the sky so thinly that your eyes can barely detect it. This is the final trick of scale. Andromeda is not small because it looks small. It looks small because our senses are limited. In reality, Andromeda is one of the largest single structures you can ever see with your own eyes. Not through a telescope, not through a photograph. With your eyes. Its true outline is simply too faint for us to notice easily. When astronomers say Andromeda is visible to the naked eye, they are technically correct. But that statement hides the deeper truth. We do not see Andromeda as it truly is. We see a tiny fraction of its light. We see only its brightest heart. The rest remains invisible, not because it is not there, but because we were not built to see it. Once you understand this, the night sky changes. You stop seeing empty space between stars. You start seeing hidden structure. You realize that the sky is not calm and sparse. It is filled with enormous, faint objects that stretch across space on scales far beyond human intuition. Andromeda is just the most dramatic example because it is both close enough and large enough to expose this illusion. So when you look up next time and spot that faint blur, remember this. You are not looking at something small and distant. You are looking at something vast and softly hidden. And if your eyes could truly see all of it, Andromeda would dominate your sky, quietly reminding you that the universe is far larger than it appears. Imagine a journey where speed is no longer the problem. No fuel limits, no engines, no waiting. Imagine you can move at the fastest speed allowed by the universe itself, the speed of light. Nothing can go faster, nothing can catch up to you. At this speed, you cross the distance from Earth to the Moon in a little more than 1 second. You reach the Sun in about 8 minutes. You cross the entire solar system in a matter of hours. Speed is no longer impressive. It is absolute. Now imagine aiming that speed toward Andromeda Galaxy, not to reach it, to travel through it. This is where scale stops being a number and becomes an experience. First, you arrive at the edge of Andromeda. There is no wall, no gate, no sign that says, "Galaxy begins here." The light does not suddenly increase. Stars do not suddenly appear in clusters. Instead, the darkness slowly changes. A few more stars appear ahead, then a few more. Then faint clouds of gas begin to glow. You have entered the outskirts of the galaxy, but nothing dramatic happens. At light speed, even entering a galaxy feels quiet. You continue forward. Minutes pass. Hours pass. You are still moving at the speed of light, yet nothing feels fast. Stars slide past you, but not like streaks in a science fiction movie. Space is too empty for that. Each star system is separated by years of distance. You pass one, then travel for years before another comes close enough to notice. There is no rush. There is only motion. After 1 year, at light speed, you have travelled 1 light year. That sounds impressive until you remember that this is the distance between neighbouring stars. 1 year, 1 star system. 1 year, another lonely sun drifting in the dark. You are not crossing Andromeda yet. You are only beginning to touch its interior. Decades pass. At light speed, decades are nothing. But emotionally, they are everything. You pass through spiral arms, regions where stars are more common. Even here, space dominates. Gas clouds stretch across thousands of light years, thin and faint. Star-forming regions glow softly, but they do not rush past. They take time. Everything takes time. After 100,000 years, you begin to understand the problem. You're still inside Andromeda. You have been moving at the maximum speed allowed by the universe for longer than all of recorded human history, and you have not crossed even half of the galaxy's visible width. The core is still ahead. The far side is unimaginably distant. The idea of crossing Andromeda begins to feel strange, like crossing an ocean that has no opposite shore. Now imagine passing star systems one by one. Each star you pass is its own world. Planets orbit quietly. Some may host life. Some may have existed for billions of years before you arrived, and will continue for billions of years after you pass. At light speed, you cannot stop, you cannot slow down. These systems appear briefly, then fade behind you, lost to time. Millions of them, hundreds of millions, and still, you are inside the galaxy. After 200,000 years, you finally cross the bright central region. This is the densest part of Andromeda. Even here, stars do not crowd together. They are simply less lonely. The glow increases. The background becomes richer. But the journey does not speed up. Light speed is already the limit. Then you move outward again. More thousands of years pass, more tens of thousands. The stars thin out slowly. The spiral arms fade. The galaxy does not end. It weakens. It stretches. It refuses to give you a clear finish line. By the time you exit the visible disk of Andromeda, more than 200,000 years have passed. You have crossed the part of the galaxy that glows, but you're still not done. Beyond the visible stars lies the halo. Dim stars, ancient and scattered, orbiting far above and below the disk. You pass through them too, light years between each one, silence between encounters, darkness that feels endless. Another 100,000 years pass, another 100,000. Only now do you begin to feel like you're leaving Andromeda behind. The stars become rare again. The background fades, but even now, gravity still reaches you. The galaxy's influence stretches farther than its light. If you include the dark matter halo, the journey becomes even longer. You may travel for more than 1 million years at light speed before Andromeda truly releases you. 1 million years. At the fastest speed possible. without slowing down, without stopping. This is the emotional shock. We are used to thinking of light speed as instant, as magical, as a shortcut through the universe. Science fiction teaches us that light speed solves distance, and on small scales it does. But on the scale of a galaxy, even light feels slow. Andromeda is so large that crossing it at light speed is not a trip. It is an era. Civilizations could rise and fall while you're still inside it. Species could evolve and disappear. Entire chapters of cosmic history could unfold while you move steadily forward, unable to rush, unable to hurry, unable to skip ahead. This changes how you feel about size. It is no longer about kilometers or light years. It is about time passing. While nothing seems to change, it is about realizing that even the ultimate speed does not make the universe feel small. It makes it feel older, deeper, more patient. Now imagine this journey not from the outside, but from within. Imagine living on a planet inside Andromeda. The galaxy is your environment. You are born, live, and die without ever leaving it. For you, the galaxy is not something to cross. It is something that simply exists around you. The idea that light would need hundreds of thousands of years to cross your home galaxy is not dramatic. It is normal. This is how the universe actually works. Galaxies are not objects we visit. They are structures we exist inside. Their scale is measured not in distance alone, but in time. Time spent traveling. Time spent waiting. Time spent moving at the fastest possible speed and still not arriving. This is why imagining light speed travel through Andromeda is so powerful. It strips away technology. It strips away limits. It strips away excuses. Even when everything is perfect, the galaxy remains vast. And that is the point. When we say Andromeda is large, we are not saying it is impressive in a technical sense. We are saying it is large in a way that overwhelms time itself, a way that turns centuries into moments, and moments into nothing. By the time you finally emerge from Andromeda's far edge, the journey will have taken longer than human civilization has existed. Longer than cities, longer than writing, longer than memory, and all you did was cross one galaxy. Not the universe, not a cluster, one galaxy. This is where scale becomes emotional. Because now size is not something you calculate, it is something you endure. And once you feel how long Andromeda takes to cross, even at light speed, you never hear the word galaxy the same way again. Up to now, Andromeda has felt enormous on its own, larger than the Milky Way, thicker than a flat disk filled with hundreds of billions of stars and wrapped in an invisible halo that stretches across space. But to truly understand its scale, we must step back even farther. We must stop thinking of Andromeda as a single galaxy floating alone and instead place it inside its cosmic neighborhood. This is where perspective changes everything. This is where Andromeda Galaxy stops feeling like just another galaxy and starts to feel like a dominant presence shaping an entire region of the universe. This region is called the local group. The local group is exactly what its name suggests, a small family of galaxies bound together by gravity. Compared to massive galaxy clusters that contain thousands of galaxies, the local group is modest. It spans only a few million light years and contains a few dozen known members. Most of these members are small faint dwarf galaxies. They are irregular in shape, low in mass and easy to overlook. Only two galaxies truly matter when it comes to size and gravity. One is our home, the Milky Way. The other is Andromeda. These two giants dominate the local group completely. Everything else revolves around them, directly or indirectly. Smaller galaxies orbit one or the other, or drift slowly between their gravitational pulls. The local group is not a balanced gathering of equals. It is a system controlled by two heavyweights, and among those two, Andromeda may be the heavier one. This is the first major realization. When we say Andromeda is inside the local group, we are not saying it is one member among many. We are saying it is one of the anchors of the entire structure. Its gravity helps define the shape, motion, and future of the group itself. To understand this dominance, imagine space not as empty, but as a landscape shaped by gravity. Massive galaxies create deep valleys in this landscape. Smaller galaxies roll downhill into these valleys and become bound companions. Andromeda's valley is deep, very deep. Around it orbit dozens of dwarf galaxies stretched into long streams by tidal forces, slowly being pulled apart and absorbed. Some of these dwarfs are already in the process of disappearing. They are being torn apart by Andromeda's gravity, their stars stripped and scattered into the galaxy's halo. These stars do not vanish. They become part of Andromeda's extended structure, increasing its size and complexity over time. This process has happened many times in the past and continues today. Andromeda has grown large, not by existing peacefully, but by consuming its neighbors. This tells us something important about scale. Andromeda's size is not static. It is the result of billions of years of growth. Now consider how far Andromeda's influence reaches. Its visible stars stretch across hundreds of thousands of light years. Its dark matter halo stretches much farther, possibly more than 1 million light years from its center. This halo defines the true boundary of Andromeda's gravitational control. Within this region, space itself is shaped by Andromeda's mass. Objects move differently, orbits bend. Smaller galaxies feel a slow, unstoppable pull inward. This means Andromeda's influence extends across a huge fraction of the local group. In fact, when astronomers model the motion of galaxies within the group, they find that many are more strongly influenced by Andromeda than by the Milky Way. Even galaxies that are not obviously orbiting Andromeda still feel its gravitational presence. It is not a local effect, it is a regional one. This brings us to an important clarification. A galaxy group is not the same as a galaxy cluster. Clusters are enormous structures containing hundreds or thousands of large galaxies. They are tightly bound, dense, and violent environments. Galaxies in clusters interact constantly. Collisions are common, gas is stripped away, shapes are distorted. The local group is nothing like that. The local group is quiet. Its galaxies are spread far apart. Interactions happen slowly. Mergers take billions of years. The distances between members are vast, and most of space inside the group is empty. This calm environment allows galaxies like Andromeda and the Milky Way to evolve gently over long periods of time. But do not confuse calm with small. Even though the local group contains relatively few large galaxies, its scale is immense. It stretches across millions of light years. And within that space, Andromeda stands out as one of the largest and most massive structures. To truly appreciate this, compare Andromeda to its neighbors. Most local group galaxies are dwarfs. Some contain only a few million stars, others only a few 100,000. They are faint, fragile systems, easily disrupted by gravity. Andromeda, by contrast, contains hundreds of billions of stars. Its mass outweighs these dwarfs by factors of thousands or even millions. This is not a fair comparison. It is like comparing a mountain to grains of sand. Even the Milky Way, impressive as it is, may be slightly less massive than Andromeda. When astronomers estimate total mass, including dark matter, Andromeda often comes out ahead. This makes it the single most massive galaxy in the local group. If that is true, then Andromeda is not just our neighbor, it is the gravitational center of our local universe. This idea reshapes how we see our place in space. We tend to think of the Milky Way as central because it is home, but gravity does not care about perspective, it cares about mass. And by that measure, Andromeda may be the dominant force shaping the future of the local group. This dominance becomes even more important when we look ahead. Over billions of years, the local group will change. Smaller galaxies will be absorbed. Orbits will shift. The Milky Way and Andromeda will move closer together, pulled by mutual gravity. When they finally merge, they will form a new larger galaxy that will dominate the region entirely. But even before that dramatic event, Andromeda already defines the group's structure. It is the largest reservoir of stars, the deepest gravitational well, the widest invisible halo. Its size is not just personal, it is contextual. Understanding Andromeda inside the local group helps us avoid another common mistake. We often imagine galaxies as isolated islands in space, each minding its own business. The reality is more connected. Galaxies exist in families. They grow by interacting. They influence one another across enormous distances. Andromeda is a perfect example of this truth. Its size cannot be measured only by its visible disk. Its importance cannot be measured only by its star count. It must be measured by how much space it controls, how many smaller galaxies it shapes, and how deeply it influences the motion of everything around it. When you place Andromeda inside the local group, its scale becomes even more unsettling. It is no longer just a large galaxy. It is one of the main architects of our local cosmic environment. Its gravity reaches across millions of light years. Its past is written in the disrupted remains of smaller galaxies. Its future includes reshaping the entire group. This is the context that changes everything. Andromeda is not just big in isolation. It is big in comparison, big in influence, big in consequence. And once you see it this way, once you understand how it towers over its neighbours and helps define an entire family of galaxies, the word neighbour begins to feel misleading. Because Andromeda is not simply nearby, it is central, it is dominant, and it quietly reminds us that even on the scale of galaxy groups, size is not about brightness or familiarity. It is about gravity, reach, and time. When people hear that Andromeda Galaxy is going to collide with the Milky Way, the word collision immediately creates fear and drama. It sounds violent, sudden, explosive. Movies and science fiction have trained us to imagine galaxies smashing into each other like cars on a highway, stars crashing, planets being thrown into chaos, and entire systems ripped apart in moments. But the real story is far stranger, far slower, and far more revealing about the true scale of the universe. This collision is not an event, it is a process. And that process unfolds over billions of years. Right now, Andromeda is moving toward the Milky Way at a speed of roughly 110 kilometers per second. That sounds fast by human standards, but on a cosmic scale, it is almost gentle. At that speed, it will still take about 4 to 5 billion years before the two galaxies truly begin to merge. To put that in perspective, complex life on Earth has existed for only a fraction of that time. The Sun itself is only about 4.6 billion years old. This collision lies so far in the future that continents will shift, climates will change, and entirely new forms of life may exist long before the galaxies touch. This is the first lesson of scale. Galaxies do not rush. They drift. The universe is patient beyond comprehension. As Andromeda and the Milky Way move closer, nothing dramatic happens at first. The night sky does not suddenly change. Stars do not rearrange themselves. For millions of years, the approach is almost invisible. The distance shrinks slowly, quietly, in ways no living creature could notice within a single lifetime. Then something subtle begins. The invisible parts meet first. Long before any stars come close, the dark matter halos of the two galaxies begin to overlap. These halos are vast, extending hundreds of thousands to more than 1 million light-years from each galaxy's center. When they touch, gravity starts to change the motion of both galaxies. Their paths curve, their mutual attraction deepens. The collision has already begun, but nothing visible has happened yet. This is crucial to understand. Galactic collisions are not about stars hitting stars. They are about gravity reshaping structure. Stars are incredibly small compared to the distances between them. Even in dense regions, stars are separated by light years. When galaxies pass through each other, the chance of two stars physically colliding is almost zero. Space is simply too empty. A galaxy collision is not like two solid objects crashing. It is like two clouds passing through each other, their shapes slowly changing under gravity. As the galaxies draw closer, tidal forces begin to stretch them. Spiral arms distort. Long streams of stars are pulled outward, forming enormous arcs that extend far into space. Gas clouds begin to compress, triggering waves of star formation. New stars are born, lighting up regions that were once dark. The galaxies do not explode. They transform, and all of this happens slowly. Millions of years pass between noticeable changes. Entire species could evolve on planets within these galaxies without ever knowing a collision is underway. From the inside, the process feels almost calm. This is where scale over time becomes more important than speed. We tend to measure events by how fast they happen. A crash is dramatic because it is sudden. A storm is frightening because it arrives quickly. But on cosmic scales, speed loses its meaning. What matters is duration. The Andromeda Milky Way merger is slow enough to feel timeless. After the first close pass, the galaxies may swing apart again. Gravity will pull them back together. They may pass through each other multiple times over several billion years. Each pass reshapes them further. Each pass strips away some structure and redistributes stars into new orbits. Eventually, after billions of years, the two galaxies will settle into a single system. Not a spiral, not two galaxies, but one new, massive galaxy. Astronomers sometimes call this future galaxy Milky, but the name matters less than the process. The final galaxy will be larger, heavier, and more spherical than either of its parents. Its spiral arms will fade, its stars will move in more random paths. It will be an entirely new structure, built from the slow blending of two giants. What is most striking is how little violence individual stars experience. Most stars will continue orbiting peacefully, just on new paths. Planetary systems are likely to survive. The night sky from any inhabited planet would change gradually, not catastrophically. Over millions of years, Andromeda would grow larger in the sky, stretching across it like a luminous river. Then it would blur and distort. Then the sky would fill with unfamiliar star patterns as the galaxies merge. This transformation would be beautiful, not destructive. The drama exists only because our intuition is built on human time. On cosmic time, the merger is gentle. This forces us to rethink what collision means. It does not mean impact, it does not mean destruction, it means interaction. It means gravity slowly rewriting the structure of space over unimaginable spans of time. And this brings us back to scale. The distance between Andromeda and the Milky Way feels large. The size of each galaxy feels overwhelming. But the true scale is revealed in how slowly these giants move toward one another. Billions of years pass and still, the process is unfinished. Light travels fast, stars orbit steadily, and galaxies drift like continents in a cosmic ocean. This is scale not measured in kilometers, but in patience. By the time the merger is complete, the Sun will likely be near the end of its life. Earth, if it still exists, will be very different. Humanity, as we know it, may be gone, replaced by something else, or by nothing at all. And yet the universe will continue, calmly merging galaxies without urgency. This perspective changes everything. The future collision is not a threat, it is a reminder. A reminder that the universe operates on timescales far beyond fear, far beyond excitement, far beyond urgency. Two of the largest structures in our local universe are moving toward each other, and it takes billions of years for anything dramatic to happen. That is the true drama. Not speed, not impact, but time. When you imagine Andromeda and the Milky Way slowly falling together, reshaping each other over cosmic ages, you begin to understand scale in a new way. Size is not just about how big something is, it is about how long it takes for big things to change. And in that sense, the future collision of these two galaxies is one of the most humbling stories the universe has to tell. There is something strange that happens when we truly think about Andromeda Galaxy. It does two opposite things to us at the same time. It makes us feel incredibly small, almost insignificant. And yet, somehow, it also makes the universe feel larger, richer, and more meaningful than before. This contradiction is not a mistake. It is the emotional signature of cosmic scale. Andromeda is not just a galaxy we study. It is a mirror that reflects the limits of human thinking, while quietly expanding the boundaries of human wonder. The first thing Andromeda does is shrink our ego. Not in a cruel way, not in a humiliating way, but in a gentle, unavoidable way. We spend most of our lives at human scale. Our world is measured in meters, hours, years, and generations. Even our greatest achievements, cities, civilizations, technologies, feel enormous only because they stretch to the limits of our experience. When we look at Earth from space, it already feels fragile. When we look at the Sun, we feel small again. And when we look at an entire galaxy, especially one larger than our own, something inside us quietly steps back. Andromeda does not care that we exist. It does not notice us. It does not need us. It has existed for billions of years before humans appeared. It will continue long after our species, our languages, and our stories have vanished. Entire civilizations could rise and fall without leaving the smallest mark on it. This realization can feel uncomfortable because it challenges the instinct to place ourselves at the center of everything. Andromeda reminds us that we are not central. Not in space, not in time, not in importance. This is where ego shrinks. The universe does not revolve around human meaning. It does not adjust its scale to fit our understanding. It simply exists, vast and indifferent, governed by rules that were written long before we arrived. But here is where the second effect begins. As ego shrinks, wonder expands. Because even though Andromeda does not care about us, we care about it. We can see it. We can study it. We can understand parts of it. The same human mind that struggles with its scale is capable of imagining it at all. That alone is extraordinary. Andromeda is a galaxy so large that light takes hundreds of thousands of years to cross it, yet it fits into human thought. Not completely, not comfortably, but enough. We can describe its structure. We can measure its motion. We can predict its future. We can tell a story about it. This is where humility turns into awe. The universe is not small enough for us, but we are large enough to wonder about it. Andromeda expands our sense of wonder because it shows us something rare. A bridge between the visible and the unimaginable. It is close enough to see with the naked eye, yet large enough to overwhelm intuition. It exists right at the edge of human comprehension. That is why it feels so powerful. It is familiar and alien at the same time. We struggle with cosmic scale because our minds were never designed for it. Evolution shaped our brains to survive on Earth, not to measure galaxies. We are good at judging distances we can walk. We understand time in seasons and lifetimes. When numbers grow too large, our intuition collapses. 1 million and 1 billion feel similar. A light year sounds impressive, but remains abstract. Our imagination works best with stories, not statistics. Andromeda exposes this limitation mercilessly. We can know its distance, but not feel it. We can know its size, but not picture it. We can know its mass, but not grasp its weight. This gap between knowledge and imagination is not a failure. It is a boundary. Andromeda sits right on that boundary, reminding us where understanding ends and mystery begins. This is why learning about Andromeda often feels unsettling at first. Each new fact stretches the mind until it feels thin. The galaxy grows larger, deeper, older, more complex. At some point, the brain stops trying to visualize and simply accepts. Acceptance replaces control, and that acceptance is important. Andromeda teaches us that not everything must fit neatly into human understanding to be real or meaningful. Some things are valuable precisely because they exceed us. They force us to approach reality with humility instead of mastery. In this sense, Andromeda becomes a reminder of limits, not limits of science, but limits of intuition. Science can measure Andromeda's rotation. It can map its stars. It can trace its dark matter halo. Knowledge continues to grow, but imagination always lags behind, and it always will. No diagram, no animation, no number can fully capture what it means for a structure to be that large. This is not something to fix, it is something to respect. Because once we accept that our imagination has limits, we become more careful with certainty. We stop assuming that the universe must make sense on human terms. We stop expecting reality to feel intuitive. And in doing so, we open ourselves to deeper wonder. Andromeda also highlights a subtle tension between knowledge and imagination. Knowledge tells us facts. Imagination tries to feel them. You can know that Andromeda is larger than the Milky Way. You can know that it contains hundreds of billions of stars. You can know that its light began traveling toward us before human history. All of this can be true and still not feel real. Imagination struggles to keep up, but imagination does not need to win. It only needs to try. Each attempt to imagine Andromeda stretches us a little more. Each failure reminds us how vast the universe truly is, and that process itself is valuable. It keeps us curious. It keeps us humble. It keeps us aware that reality is bigger than comfort. This is why Andromeda makes the universe feel both small and big. It makes us feel small because it removes us from the center. It makes the universe feel big because it shows us how much more exists beyond us. And somehow, these two feelings do not cancel each other out. They coexist. We are small, but not meaningless. The universe is vast, but not empty of wonder. Andromeda does not diminish humanity. It reframes it. It places us where we actually belong, not at the center of the universe, but as observers capable of curiosity, reflection, and awe. In the end, Andromeda is not important because it is large. It is important because it teaches us how to think about largeness itself. It forces us to confront scale honestly, without shortcuts. It reminds us that the universe is not built to be understood easily, and that this difficulty is not a flaw but a feature. When you look at Andromeda and feel both insignificant and amazed, that feeling is not confusion. It is clarity. It is the feeling of standing at the edge of human understanding and realizing that the universe is bigger than any story we tell about it, yet still willing to be explored. And that may be Andromeda's greatest gift. Not answers, not comfort, but perspective. A perspective that quietly tells us, you are small, but you're thinking about something vast, and that alone is extraordinary. There is nothing wrong with misunderstanding Andromeda. In fact, misunderstanding it is almost unavoidable. The galaxy is too large, too distant, and too different from everyday experience for intuition to work naturally. Most of what people believe about Andromeda Galaxy comes from images, movies, and simplified diagrams. These sources are not trying to deceive anyone. They're trying to make something impossibly large feel manageable, but in doing so, they quietly introduce ideas that are not quite true. This part is not about correcting mistakes with embarrassment or judgment. It is about gently clearing away mental shortcuts that no longer help once we begin to think seriously about scale. One of the most common misunderstandings comes directly from movies and visual media. Galaxies are often shown as crowded, glowing structures where stars sit close together, lights packed tightly into swirling patterns. Space looks busy, motion looks fast, everything feels energetic and dense. This makes sense visually. A sparse galaxy would not look impressive on screen. But the Real Andromeda is nothing like this depiction. Galaxies are not dense. They look dense only because of how images compress space. In reality, Andromeda is mostly empty. The distance between stars is enormous, even in its brightest regions. If you were traveling through the galaxy, you would not pass star after star in rapid succession. You would pass one, then spend years traveling through darkness before encountering another. The glow we see in images comes from the combined light of countless stars spread across huge distances, layered along our line of sight. What appears crowded is actually deeply spaced out. This misunderstanding is especially strong because we naturally compare galaxies to cities. Cities are dense, buildings are close, lights cluster together. But galaxies are not cities. They are more like continents scattered across oceans of emptiness. The lights are real, but the space between them defines the structure far more than the lights themselves. Another widespread misunderstanding is the idea that galaxies spin like solid objects. We often imagine Andromeda rotating like a vinyl record or a spinning plate, with every part moving together at the same rate. This image feels natural because solid objects behave this way. But galaxies are not solid. They're collections of independent objects, bound only by gravity. Each star moves on its own path, responding to the combined gravitational pull of everything else. Andromeda does rotate, but not as a single rigid structure. Stars closer to the center orbit differently than stars farther out. Some move faster, some move slower, some follow tilted orbits above or below the main disk. Gas clouds behave differently than stars. Dark matter shapes motion invisibly. The spiral arms themselves are not fixed structures. They are more like traffic patterns, regions where stars and gas temporarily bunch up before moving on. This matters because imagining a galaxy as a solid spinner hides its true complexity. It makes the galaxy feel simpler than it is. Andromeda is not a machine. It is a dynamic system, constantly changing, never repeating the same configuration twice. Then there is the idea of the edge. People often ask, where does Andromeda end? This question makes perfect sense from a human perspective. Everything we interact with has an edge. A table ends, a forest ends, a country ends. So we expect galaxies to have edges too. Bright spiral arms stop, and then space begins. But edge is the wrong word. Andromeda does not end. It fades. The visible stars become thinner. The glow weakens. Stellar density drops. But there is no sharp boundary where the galaxy suddenly stops existing. Beyond the visible disk lies the stellar halo. Beyond that lies the dark matter halo. Even farther out, Andromeda's gravitational influence continues to shape motion in space. Asking where Andromeda ends is like asking where the atmosphere ends. At some point, air becomes so thin that it blends into space, but there is no sudden cutoff. The same is true for galaxies. Their boundaries are gradual, not abrupt. Textbooks often simplify this by drawing clear outlines. This is useful for teaching basic structure, but it creates a false sense of precision. It trains the brain to think in borders when the universe operates in gradients. Another misunderstanding comes from how galaxies are compared. We often see diagrams showing the Milky Way and Andromeda side by side, neatly scaled, floating in black space. This creates the impression that they are similar in size, neatly separated, and easily compared. But these diagrams hide depth, hide halos, and hide influence. They show only the brightest parts and ignore the invisible mass that dominates both galaxies. In reality, Andromeda's dark matter halo may overlap with that of the Milky Way. This means the two galaxies are not as separate as diagrams suggest. Their gravitational reach may already be touching. The clean separation we imagine does not exist on the deepest level. Movies also contribute to another major misunderstanding. They often show galaxy collisions as violent, fast, and catastrophic. Stars crash, systems explode, everything happens at once. This makes for exciting storytelling, but it completely misrepresents reality. As we explored earlier, galaxy mergers are slow and gentle on the scale of individual stars. Space is too empty for frequent collisions. Most stars pass by each other peacefully, reshaped only by gravity over long periods. This misunderstanding feeds fear. People hear that Andromeda will collide with the Milky Way and imagine destruction. In reality, the merger will be one of the calmest large-scale events the universe can produce. Dramatic in shape, dramatic in time, but not violent in the way our instincts expect. Another subtle misconception is that brighter means more important. Because Andromeda's core is bright, people assume it is the most massive or dominant part of the galaxy. But brightness does not equal mass. The brightest regions are not necessarily the heaviest. Much of Andromeda's mass lies in dark matter, which does not glow at all. The most important component of the galaxy is invisible. This flips our intuition upside down. We are trained to value what we can see. The universe often operates on what we cannot. One more misunderstanding deserves special attention. Many people believe that because Andromeda is far away, it must be small in some absolute sense. Distance and size become tangled together. Something distant feels reduced. This is how everyday vision works. A mountain far away looks small, but cosmic scale breaks this rule. Andromeda looks small because it's faint. Not because it's small, its apparent size in the sky is actually enormous when measured properly. This confusion is not foolish, it is built into human perception. Our eyes evolved to judge nearby objects. They are not designed to separate brightness from size across millions of light years. Andromeda exploits this weakness perfectly. It hides its enormity behind faint light. It is important to say this clearly. None of these misunderstandings mean people are ignorant or careless. They mean the universe is unintuitive. The language we use, the images we rely on, and the metaphors we choose all struggle to keep up with cosmic reality. Simplification is necessary to begin learning, but eventually those simplifications must be revised. Andromeda is often the first place where people encounter this need to unlearn. Unlearn the idea of density, unlearn the idea of sharp edges, unlearn the idea of solid rotation, unlearn the idea that what we see is all that exists. Doing this does not make the universe colder or less beautiful. It makes it deeper, more honest, more interesting. The goal is not to replace wonder with correction, but to refine wonder so it aligns with reality. When you understand that galaxies are mostly empty, mostly invisible, and mostly governed by slow gravity rather than fast motion, Andromeda becomes even more impressive, not less. It transforms from a pretty picture into a complex evolving system that challenges human intuition at every level. And perhaps the most important misunderstanding to clear away is this one. That understanding Andromeda fully is possible. It is not. We can measure it, we can model it, we can describe parts of it, but no single image, explanation, or story can capture its true scale. The galaxy is simply too large, too layered, and too patient for complete understanding. And that is not a failure. It is an invitation to keep questioning, to keep refining mental models, to accept that some things will always stretch beyond comfort. Andromeda teaches us this gently. It does not demand that we understand it perfectly. It simply exists, quietly challenging our assumptions every time we try to reduce it to something familiar. Once these misunderstandings are cleared away, not with shame but with curiosity, we are left with something better than certainty. We are left with respect for scale, respect for complexity, respect for a universe that refuses to fit inside human shortcuts. And that is the clearest understanding Andromeda can offer. When we step back from numbers, images, and comparisons, Andromeda Galaxy begins to teach us something deeper than astronomy. It teaches us about reality itself, Not reality as we experience it in daily life, but reality as it truly exists, independent of human senses, intuition, or comfort. Andromeda forces us to confront scale not as a poetic idea, but as a scientific problem. Scale determines how gravity behaves, how galaxies form, how time unfolds, and how the universe evolves. Without understanding scale, physics itself breaks down. The laws of nature do not change from place to place, but their effects do dramatically, depending on size, distance, and time. Andromeda sits at a scale where everyday intuition completely fails, and that failure is not a weakness of science. It is a feature of reality. In science, scale is not decoration, it is structure. The same physical laws govern an apple falling from a tree and galaxies colliding across millions of light years, but the outcomes look nothing alike because scale reshapes everything. Gravity between two small objects feels weak and predictable. Gravity, acting across the mass of an entire galaxy, becomes the architect of structure itself. Andromeda teaches us this by existing. Its spiral arms, its rotation, its dark matter halo, and its future merger with the Milky Way are all consequences of scale. If Andromeda were smaller, it would behave differently. If it were larger, it would behave differently again. Understanding its size is not optional. It is the only way to understand why it looks and moves the way it does. This is why size changes physics. At human scale, motion feels fast, events feel sudden, causes and effects appear close together in time. At galactic scale, motion becomes slow, almost frozen. Events unfold over billions of years. Cause and effect stretch across cosmic ages. Andromeda shows us that speed is relative, not just to velocity, but to scale. What feels slow to us is fast for a galaxy. What feels eternal to us is brief in cosmic history. The galaxy has existed for billions of years, quietly forming stars, absorbing smaller galaxies, and reshaping itself long before humans learned to write. It will continue doing so long after our species is gone. Time, when viewed through Andromeda, stops being something we count and starts being something that flows on scales far beyond memory. Galaxies also reshape our understanding of time by revealing how patient the universe is. The future collision between Andromeda and the Milky Way is not a dramatic countdown. It is a slow convergence measured in billions of years. Nothing in human experience prepares us for this. We think in deadlines, lifetimes, and generations. The universe thinks in eras. Andromeda exists comfortably in that time scale. It does not hurry. It does not resist. It simply follows gravity's instructions over unimaginable spans of time. This teaches us that urgency is not a property of reality. It is a property of human life. Andromeda also exposes a deeper truth. The universe is not built for intuition. Our intuition evolved to help us survive on a planet, not to understand galaxies. We expect edges, solids, clear motion, and immediate cause and effect. Andromeda offers none of these. It has no clear edge, only a gradual fading. It is not solid, only loosely bound by gravity. It does not spin like an object, but flows like a system. Its most important mass is invisible. Its light lies to our eyes by appearing small while being vast. Every instinct we bring to it fails unless corrected by careful thinking and evidence. This is not a flaw in human intelligence. It is a mismatch between scale and biology. Science exists to bridge that mismatch. Through observation, measurement, and theory, science allows us to reach beyond intuition and touch reality as it actually is. Andromeda is a perfect example of why this matters. Without science, it would remain a faint smudge in the sky, a curiosity at best. With science, it becomes a structure hundreds of thousands of light years across, wrapped in dark matter, dominating a galaxy group and shaping the future of our cosmic neighborhood. Knowledge transforms Andromeda from an image into a system, but knowledge alone is not enough. There is a difference between knowing facts and understanding meaning. Andromeda teaches us that meaning emerges when we accept the limits of imagination. We can calculate its mass, but we cannot feel its weight. We can measure its size, but we cannot truly picture it. And that gap is important. It reminds us that reality does not owe us comfort or clarity. The universe is under no obligation to fit inside human intuition. This realization leads to humility. Not the humility of weakness, but the humility of honesty. Andromeda humbles us by showing how small our perspective is, not how small we are as beings. There is a difference. We are small in size, yes, but we are remarkable in our ability to question, observe, and understand. A creature that evolved on a small planet around an average star can think about a galaxy millions of light years away and uncover its structure. That is not insignificance, that is perspective. Humility through science does not mean shrinking ourselves into nothing. It means placing ourselves accurately. It means recognizing that our stories, fears, and ambitions unfold on a tiny stage within a universe of unimaginable scale. Andromeda does not diminish human meaning. It reframes it. It tells us that meaning is not about dominance or centrality. It is about awareness. Understanding Andromeda also teaches us restraint. When we realize how large and old the universe is, we become more careful with certainty. We stop assuming that what feels obvious must be true. We stop expecting reality to behave intuitively. We become more patient with complexity. Science, at its best, is an exercise in disciplined humility. Andromeda rewards that discipline by revealing more depth the longer we study it. There is another quiet lesson here. Scale teaches us connection. Andromeda is distant, but it is not disconnected. Its gravity already influences our galaxy. Its future is intertwined with ours. The Milky Way and Andromeda are not isolated stories. They are chapters in the same cosmic narrative. This reminds us that separation in space does not mean separation in consequence. The universe is deeply interconnected, even across millions of light years. In the end, Andromeda teaches us that reality is layered. What we see is not what exists. What we feel is not what matters. What we intuit is not what is true. And yet, through careful observation and honest reasoning, we can still learn. We can still understand enough to be changed by that understanding. That may be the most important lesson of all. The universe is not built for intuition, but it is open to inquiry. Andromeda stands as proof. A galaxy too large to imagine, too distant to visit, too complex to fully grasp, yet close enough to see and study. It reminds us that reality is vast, patient, and indifferent, but not unreachable. Science does not make the universe smaller. It makes us wiser about how big it truly is. And in that wisdom lies humility, wonder, and a deeper respect for a reality that continues to stretch far beyond the limits of human thought.